This is lecture 21 on urban transportation planning. We will continue our discussion on trip distribution analysis in this lecture. You may recall in the previous lecture we started our discussion on trip distribution analysis with the understanding that trip distribution is nothing but the process of synthesis of trip interchanges between traffic zones. We also found that it is convenient to present trip distribution data in the form of a matrix, and we discussed about two types of matrices: PA matrix giving information about zonal trip productions and zonal trip attractions, as well as OD matrix giving information about trip origins and trip destinations. Then we understood the procedure of converting PA matrix into OD matrix, and then we try to identify the factors that influence distribution of trips between traffic zones, and based on the identified factors we found that Newton's law of gravitation can be considered as a basis for framing an analytical formulation in the form of a model to explain trip distribution, right? And with this understanding, to check our effectiveness of recapitulation of the points in the previous lecture, let us pose a few questions to us and try to answer. The first question is this: what is the need to convert PA matrix into OD matrix? Any response? Why should we convert PA matrix into OD matrix?
Trip assignment, which is the next step of fourth step of the modeling process, is
yes,
trip assignment. In that we need only OD matrix. PA matrix won't be helpful.
That is the point. So we need to know the direction of movement between traffic zones while we do traffic assignment or route assignment in the fourth and last step of the planning process. So that is the reason why we need to convert PA matrix into OD matrix, and we should be conversant with the procedure. The next question is this: what are the factors that influence the distribution of trips between traffic zones? Factors influencing distribution of trips between traffic zones. Anybody?
Travel time and generalized cost. Generalized cost includes the aggregate money value, that is including the travel time, out of pocket cost, and level of comfort.
Yes, what you mean is the generalized cost of transportation is a major factor influencing trip distribution. That is one of the factors. There are other factors that influence distribution of trips between traffic zones. We discussed about the relative attractiveness of traffic zones, the amount of trips produced and attracted by different traffic zones. When the amount of trip attracted by a zone is large, obviously such a zone is likely to attract more trips from various other zones. Similarly, if a zone is producing large number of trips, the distribution of trips from that zone is likely to extend over vast area covering more number of traffic zones, isn't it? So that way we need to understand both the amount of trips produced, amount of trips attracted, as well as some factor representing spatial separation between zones are the major factors. We represent the spatial separation using the generalized cost of transport, which involves out of pocket expenditure, travel time, travel cost, comfort, convenience and so on, all transformed into money value, is not it. So, that is how we need to understand the factors influencing trip distribution. Basically there are 3 factors: trip production, trip attraction and generalized cost of transportation. Then can anyone state the Newton's law of gravitation? Put up your hands if you are ready. Newton's law of gravitation. Newton's law of gravitation states that the force of attraction between 2 bodies is directly proportional to the product of the masses of the 2 bodies and inversely proportional to the square of the distance between the 2 bodies, is not it. That is the statement of Newton's law of gravitation. And mathematically we can give Newton's law of gravitation in the form of equation as given in equation 1. Force of attraction F is equal to k times m1 into m2 divided by r square. R is the distance between the 2 bodies, square of r is given in the denominator, and k is the proportionality constant, because we represent Newton's law in the form of an equation here, right. The same principle can be applied to develop a model to explain trip distribution. The application of this concept to trip distribution takes a form: Tij is equal to k times Pi Aj divided by Wij raised to power c. Trip productions and attractions of the zones replacing the masses m1 and m2, is not it, of the bodies, and the travel impedance, which is a proxy for generalized cost of transportation, all the same, travel impedance or generalized cost of transportation between zones taking the place of r. Otherwise structurally this equation is similar to equation 1. The exponent of the impedance term, the denominator, however, does not need to be exactly equal to 2 as in equation 1. It can take any value depending upon the actual field conditions. We have to really calibrate and find out the exact value of c, value of the exponent. May be replaced by a model parameter as shown here, c, because it is going to be a variable and it should be actually derived based on calibration. From the equation 2, previous equation, Tij to be equal to k times Pi Aj divided by Wij raised to power c implies that the interchange volume between a trip producing zone I and a trip attracting zone J is directly proportional to the magnitude of the trip productions. That is very important. The actual magnitude of the trip productions of zone I and the trip attractiveness, or again magnitude of the trips attracted, attractiveness of zone J, and inversely proportional to a function of the impedance Wij between the 2 zones in any zonal pair. Clear? That is the meaning of the previous equation. And the same equation or the same statement that we made just now can be understood in a mathematical format like this. It can be said that the interzonal volume Tij, interzonal volume is nothing but the Tij in the equation, is the dependent variable. The productions Pi, attractions Aj and the travel impedance Wij raised to power c are the independent variables, is not it, and the constants k and c are the parameters of the model that must be estimated through calibration using a database. Let us say we are trying to calibrate a trip distribution model for base year condition. In the base year you will have information about the actual trip distribution between zonal pairs that can be collected, and it is possible to get Tij value for your study area, and Pi Aj values also will be known to you. So, you have values for Tij, Pi and Aj. Using these values it is possible to find the values for the terms k and c, and this process is what we call as calibration of trip distribution model. Of course, the parameter k can be eliminated from equation 2 by applying trip production balance constraint, which states that the sum over all trip attracting zones j, right, of the interchange volumes that share I, trip producing zone I as a trip producing zone, must equal the total trip production of zone I. You may recall when we discussed the convenient format of presenting trip distribution data, we discussed about PA matrix. We also know that if you add the cell elements along a row, you will be getting the total trip production pertaining to that particular zone. We will be adding T 11, 12, 13, 14 and so on up to 1n. Then sum of all the cell values will give the total trip production for zone 1, P1 will be obtained, right. So, that is the information we have, and use this formulation as a constraint in equation 2, and let us see how we can modify equation 2 using this constraint. This is a statement. When we say that sum of all the cell values along a row is this much, it is nothing but Pi is equal to sigma j equal to 1 to n Tij. Tij is nothing but a cell value, right. When you add cell values from 1 to n, you get Pi value, total trip production. Now substitute the value of Tij from the previous equation. In equation 3 we get Pi can be written as sigma j is equal to 1 to n k times Pi Aj divided by Wij raised to power c. Agreed? We are substituting the value of Pi, just let us go back and see. This is what we do, and we know the value of Tij from equation 2. As per equation 2, Tij is what? Is equal to sigma k times Pi Aj divided by Wij raised to power c. That is what we do. We simply substitute that value instead of Tij in this equation, and you get this form. Pi becomes sigma j is equal to 1 to n k times pi aj divided by wij raised to power c. Let us call this equation as equation 4, and we can simplify this. Sigma is over j only, isn't it, and k and pi will not have any effect as far as the summation is concerned. Take those two quantities outside the sigma sign, and you can write pi to be equal to k pi into sigma j is equal to 1 to n aj wij raised to power c, and pi gets cancelled on both sides, and we get simply 1 to be equal to k times sigma j is equal to 1 to n aj divided by wij raised to power c. From this, k can be written as 1 by sigma j is equal to 1 to n, right, aj by wij raised to power c, or you can give the same information in a different form. Instead of writing 1 by, you can say raised to power minus 1. That is what I have done. From equation 4, k can be written as k equal to sigma j is equal to 1 to n aj by wij raised to power c, the whole thing raised to power minus 1. Let us call this equation as equation 5. Now, the expression for k ensures that the trip balance equation is satisfied. Do you agree with this statement? The expression for k ensures that the trip balance equation is satisfied. What do you understand by trip balance equation? It is nothing but the fact that sum of all the cell values in the matrix along a row is equal to the total trip production for a particular traffic zone, and that was given as the input. That information was given as input, and finally we have just got the value of k to be this much. That is the implication. So, we have got the value of k using that particular constraint, the form of aj or involving aj and wij raised to power c, right. Try to put this value of k in the original equation that we got for Tij, equation 2. Tij is equal to sigma j is equal to 1 to n k times pi aj divided by wij raised to power c. So, that k within sigma is going to be replaced by this quantity. If you do so, we will get this equation, right. So, we can write Tij to be equal to 1 by sigma j is equal to 1 to n aj divided by wij raised to power c into pi aj whole divided by wij raised to power c, isn't it. I am simply substituting the value of k from equation 5, the previous equation, in equation 2, and this leads to the classical form of gravity model. Clear? And if you can modify and write the same equation in a compact form, you can take Fij to be equal to 1 by Wij raised to power c. This is just for convenience. Okay, we change or take 1 by Wij raised to power c as Fij, and the calibration constant c is now implicit in the friction factor Fij. That is the point, because we take Fij to be 1 by Wij raised to power c. That means when you estimate the value of Fij, you actually estimate the value of c. That is the implication. Then using Fij instead of 1 by Wij raised to power c, we can write the previous equation in a compact form like this. Tij can be written as Piaj Fij divided by sigma j is equal to 1 to n Aj Fij, right. And so the gravity model of trip distribution can be remembered in this form. Tij, trip interchange between zones I and j, a number of trips interchanged between zones I and j is given by Pi, trip production in zone I, Aj, trips attracted to zone j, into a friction factor Fij whole divided by sum over j from 1 to n of the product of Aj and Fij. Please remember, friction factor is zonal pair specific Fij, it should be like that, isn't it. Travel impedance cannot be same for all zonal pairs, it should be specific to a zonal pair under consideration, that is why it is Fij. Clear? And finally, a set of interzonal socio-economic adjustment factor given by notation small kij, lower case kij, are introduced during calibration to incorporate the effects that are not captured by the limited number of independent variables included in the model. We have just only 3 independent variables in this model. Tij is the dependent variable, Pi, Aj and Fij, which indicates the travel impedance, or the independent variable. Sometimes it may not be possible to explain the trip interchanges Tij with these 3 independent variables also only, right. In that case, there may be a need to introduce a factor given by the notation Kij to take care of the unexplained part of the distribution of trips between zones by the 3 independent variables. Will it happen like this in practice? You consider the case of 2 traffic zones wherein in one zone there is a huge employment attraction center, let us say public sector manufacturing plant like BHEL factory employing more than 10,000 employees. And normally it is the practice in India that large scale public sector undertakings develop residential quarters also for the employees to accommodate as much of the employees as possible. Normally more than 80% of the employees of public sector undertakings are residing in the quarters of that particular company. And when they develop such residential quarters, they will see that they are as close to the employment place as possible, so that commuting time can be reduced. While acquiring land for the factory itself, they will keep this residential requirement in mind, and they will acquire contiguous land spaces both for the employment location as well as for residential location. So when you come across such a situation in an urban area, then you will find that a large number of work trips are attracted between these 2 zones, employment center in one zone and large residential colony in another zone. There will be a large number of trip attractions or trip interchanges between these 2 zones compared to all other zonal pairs. So this is a special case. Your model developed based on trip interchanges over the entire urban area may not be able to explain this particular situation. So, in such case you must check to what extent it is higher than the normal average trip interchange, and then to compensate for that introduce a coefficient indicated by Kij for this particular zonal pair. If trip interchanges among majority of other zonal pairs are matching with the average that you get using the model, then you can take Kij to be simply 1, it will not make any difference. Maybe in that particular case you may have to take a Kij value much higher than 1, maybe 2 or 3 depending upon the situation. And other possible examples are, there may be a particular religious or ethnic group of people living in one traffic zone. Their place of worship might be located in a different traffic zone. Then you will find that there is large number of trip interchanges between these two zones compared to the average trip interchange in zonal pairs in an urban area, right. So, these are all the situations which may not be effectively explained by the general gravity model. So, that is the purpose of introducing this particular factor indicated by small Kij, zone to zone adjustment factor, to take into account the effect of socio-economic connectivity between zonal pairs. Okay. Then the resulting gravity model formula becomes as given in equation 8. Tij has to be written as Pi Aj Fij Kij, zone to zone adjustment factor, divided by sigma j is equal to 1 to n Aj Fij Kij. We are introducing Kij both in the numerator as well as in the denominator. The general formulation of the gravity model, very general formulation, we are trying to generalize it further, can be written like this. Please note, we have written Tijk, there is one more subscript Tijk, and we have introduced a superscript for T, in fact it is Tmijk is equal to Pi Ajk. For trip attraction also we are introducing the subscript k, Ajk Fij m or Fmij we can say into Kij whole divided by sigma j is equal to 1 to n Ajk again Fmij Kij whole thing within brackets, and for the bracketed quantity we are given a subscript p. So, this is a very generalized formulation of gravity model. That is reason for introducing all these subscripts and superscripts. Tijkm is this: trips produced in zone I and attracted to zone J by mode m in kth iteration. Fijm is empirically derived travel time factor or friction factor for mode m, for a specific mode, for mode m, which expresses the average area wide effect of spatial separation on trip interchange between zone I and zone J. K is iteration number and P trip purpose. This is a very general form of the gravity model. Now we should be very clear to answer the following questions. Should we have to do trip distribution based on the mode used for trip making? Is it necessary? Any response? Why not put the trips made by all the modes together and distribute the trips as simply person trips? Is it necessary to distribute trips based on mode used for travel? Necessary or not? Of course, the equation implies that it is necessary. You consider trips made by foot, walk trips. What will be the extent of distribution of trips from one traffic zone? Maybe it may extend over the adjoining traffic zones, the distance involved being not more than 1.5 or 2 kilometers maximum. So distribution zone is becoming small and the zonal pairs involved are going to be adjacent zonal pairs. If we consider trips made by bicycle, it may extend a little more, covering few more zones, but still the distance covered may not be normally more than 5-6 kilometers, right. That will be the region of distribution of trips by that particular mode of bicycle. If we consider public transport trips, it may extend widely, covering the urban area which is covered by the route of operation by the transit service. There may be areas where you do not have good public transit service, and if you take the trip interchange using personal motorized vehicles like motorcycle, car, the trip interchange distance involved and the pattern will be totally different. So we should be convinced that trip distribution should be done after segmenting data based on mode used for travel. That is why we discussed mode choice analysis first before getting into trip distribution analysis, right. It will be more accurate and appropriate if you distribute trips based on mode used for travel. Additionally, it will be more appropriate if you segment data further based on the purpose of trip purpose. If you take trips made for work, the employees have no control of the location of the workplace. Some employees may have to travel very long distance, commute very long distance for work, some may have to travel medium distance and short distance and so on. These are mandatory trips, and the distribution pattern of trips for work will be totally different from the distribution pattern of trips for shopping, for example, from a particular zone. Shopping, we have the choice of going to this place or that place depending upon our need and weight of the purse. Okay, you cannot say that shopping trip distribution will be similar to work trip distribution. Similarly, trips made for education will have a different pattern, may not be as long as the work trips, may be slightly less than the length of the work trips, because you have some choice, limited choice for fixing your place of education for the wards, right. So it is appropriate to segment your data based on trip purpose also. If you segregate data based on mode used for travel and within that the trip purpose, you will be getting highly homogeneous database for calibrating your trip distribution model, which will be very effective in predicting the future trip distribution. So that is the idea of introducing M and P. Then why K, iteration number? Why should we do iteration in getting Tij value? please remember we have introduced one constraint already in this model formulation with regard to trip production. The sum of the cell values along the row should be equal to total trip production. That constraint was taken into the modeling process itself. We derived K value based on that constraint. So, this formula will give a result which will give this the total of cell values to be total trip production, will not be any change. But there is another constraint related to the trip distribution matrix. The column totals, cell values along a column should give you the total trip attraction by each of the traffic zones, but this constraint was not brought into your model formulation, right. So, when you use this gravity model or when you try to theoretically explain trip distribution, you may get some trip distribution pattern or some cell values for each of the matrices that will adhere to the condition that along a row the total of the cell values gives you the total trip production, but need not adhere to the another constraint, namely the cell values along a column should be equal to the trip attraction for the traffic zones. That will not be adhered to because that constraint has not been brought into our model formulation, right. We are trying to explain theoretically the trip distribution process and try to get the cell values in the matrix finally. And since we have introduced one constraint, so trip production values will not get affected in the result, trip attraction values will change, there will be some changes, and we must try to bring those attraction values also to match with the actual observed attraction values by some iterative process, right. That is why, or to imply that, we have introduced the subscript K here, and K is introduced in respect of Tij and Aj only, you can look at, because it is related to attraction. Iterative process will influence Aj value which will result in a change in Tij value, that is why iteration is necessary, clear. And with this understanding, let us take a very simple numerical example and see how gravity model can be applied to this particular case. The number of work trips produced in and attracted to 3 zones 1, 2 and 3 by public transit or as under, clear. Now, the segmentation information is already given to you. This pertains to work trips, data is already segregated based on trip purpose, and mode is public transit. So, what you get here is segmented data at 2 levels, one based on mode used, other one based on trip purpose, okay. Already data given to you is segmented, clear. Zone number, trips produced Pi and trips attracted Aj. Zone 1 produces 14 trips and attracts 33 trips. Zone 2 produces 33 trips, attracts 28 trips, and zone 3 produces 28 trip ends in fact and attracts 14 trip ends, and total of the trip ends produced and attracted are 75 each. This information given to us. These trip ends pertain to trips made for work by public transit. The friction factor Fij, values between the various zones obtained as a result of calibration, can be taken from the following matrix. The calibration result is also given to you because we are trying to understand the application of gravity model in this case. So, you have been given the result of calibration. Fij values for the different zonal pairs are given to us. These are the Fij values. As I told you, friction factor is specific to zonal pairs. So obviously it will be in the form of a matrix, and this is what we need to do: distribute the trips between the zones, taking the zone to zone adjustment factor Kij to be equal to 1. Further simplification, since we have only 3 zones, it is found there are no special socio-economic factors that deviate or gives you significantly different value compared to what you will be getting by using the gravity model. So Kij can be taken to be 1 for all the 3 zonal pairs. Clear? So this is the information given. So it is going to be direct application of the given values in the equation for trip distribution. The general form of the gravity model for this case can be written as follows. I am not given the superscript m because mode is already given to us. I have also removed the subscript p at the bottom of the bracket because the purpose is also given to us. We distribute trips made for work, and within work trips made by public transit. Clear? So m and p are gone. We are not introducing those subscript as well as superscript. So we can write Tijk to be equal to Pi Ajk Fij Kij whole divided by sigma j is equal to 1 to n Ajk Fij Kij. And what is the value of Kij in this case? Kij has been given as 1. The value of zone to zone adjustment factor is 1 and the value of n is 3. We have only 3 zones. So we can further simplify this equation based on the fact that Kij is equal to 1 and number of traffic zones are only 3. We can write Tijk to be simply equal to Pi Ajk Fij divided by j is equal to 1 to 3 Ajk Fij. Now we have been given the values of Pi, Aj as well as Fij. Friction factor values are also given, right, and we need to work out only Tij values. Clear? Simply substitute the corresponding values in this equation. Accordingly, we can write T11 intrazonal trip distribution within traffic zone 1 to be P1 A1 F11 divided by A1 F11 plus A2 F12 plus A3 F13 and substitute the values 14 into 33 into 13. 14 is Pi value, 33 Aj and 13 Fij whole divided by 33 into 13 plus 28 into 82. 82 is again Fij value plus 14 into 41, that is equal to 1.82. It is a fraction. We will have the fraction as it is at this stage, and finally we have to round it off to the nearest whole number, because Tij is nothing but the number of trips distributed between traffic zones. It cannot be in fraction. Since we are the middle of the analysis, we need not have to worry about rounding the fractional part to the whole number at this stage. Similarly, T12, since denominator is same, I am just putting the final value of the denominator, numerator only will change. 12 is 14 into 28 into 82 whole divided by 3299, that is equal to 9.74, right. And then T13 between 1 and 3, 14 into 14 into 41 whole divided by 3299, same denominator, which gives you a Tij value of 2.43. So T11 1.8212 9.74 13 2.43, that is our interest. This is distribution of trips from one to other zones. And similarly, let us do the calculations for zone 2, 1, 33 into 33 into 50. 33 stands for what? 21 is nothing but Ij, Tij. Obviously 33, the first 33 stands for production in zone 2, and next 33 stands for attraction in zone 1, and 50 is F12, the friction factor for travel between 1 and 2, isn't it, from 1 to 2, right. Whole divided by 33 into 50 plus 28 into 26 plus 14 into 39, that gives you a value of 18.62 trip interchanges between 2 and 1. T22 intrazonal trip interchanges in zone 2, 33 into 28 into 26 whole divided by the same denominator 2924 gives a value of 8.22. Then T23 33 into 14 into 39 whole divided by 2924 6.16. So from zone 2 we have trip interchanges of 18.62, 8.22 and 6.16. Similarly from zone 3, T31 is 28 into 33 into 50 whole divided by 33 into 50 plus 28 into 20 plus 14 into 41, that is equal to 16.59 trip interchanges between 3 and 1. T32 28 into 28 into 20 whole divided by 2784, that is equal to 5.63. T33 28 into 14 into 41 whole divided by 2784, 5.77, right. So we have done the calculations involving all the 3 traffic zones. Let us put these numbers in a matrix form and take a overview and check whether we have arrived at the final result or we need to do some more iterations, right. This is the result given in matrix form. T11 12 13, T21 23, right, 22, and T31 32 and 33, isn't it? That is what we calculated. And if you look at the sum of the cell values along rows, you get the numbers as 14, 33 and 28 trip production values for zones 1, 2, 3 or respectively 14, 33 and 28. These are the actual given values to us initially when we started applying the gravity model. There is no change in the PA values, whereas if you look at the total of the cell values along columns we get values of 37.03 for zone 1, 23.59 for zone 2 and 14.37 for zone 3. What were the actual values of attraction for zones 1, 2 and 3? Now what do we do with this result? Can we say that this distribution is acceptable? It is not, because the distribution process should not distort the basic values of trip production and attraction. Your trip attraction, zonal trip attraction values are distorted because of the distribution process. The reason is we have assumed a set of independent variables to be influencing the trip distribution and use those independent variables to get trip distribution. And in the development of the model, we introduced one constraint to see that the total of the cell values along a row gives you trip production. That constraint was introduced in the model. That is how we are getting undisturbed values, unchanged values of trip production for the zones. The other values, trip attraction values, are changed now. We must resort to some iterative process to see that the trip attraction values also brought back to the original values, simultaneously holding trip production values unchanged. That will be held because it is in the model framework itself. Okay. And let us see how to go about doing this. Of course, the statement is given here. It can be seen that the total trip productions after that distribution match with the corresponding predicted values, but the attractions do not equal, right, the predicted attractions. Further iterations are therefore necessary. Now the question is how to go about doing the iteration. Our main objective is to push these distorted values close to the actual observed value for each of the zones. That is our intention, right. So this is how we do the iteration. The following formula can be used to adjust trip attraction values for subsequent iterations. We say Ajk to be equal to Aj divided by Cjk minus 1 into Ajk minus 1, where Ajk is equal to adjusted attraction pertaining to iteration k, right. Aj desired attraction, which was originally the input for the model, desired attraction. Ajk minus 1 adjusted attraction pertaining to iteration k minus 1. Cjk minus 1 is equal to calculated attraction as per iteration k minus 1, right. So we have some value of trip attraction as a result of the calculation, indicated here as Cjk minus 1. That is what we get as the total of the cell values along each column at the end of the calculation, right. That is indicated here as Cjk minus 1. Ajk minus 1 is nothing but the attraction values given initially for that particular iteration as trip attraction values. Aj is the desired value which was obtained originally as trip attraction values for your traffic zones, right. Let us say your calculated value is small compared to Aj value, desired value, then you may have to increase the trip attraction value by some means, right. That is what we do. See, when we have a smaller value in the denominator, corresponding to the observed value and multiply that by the trip attraction value that you have given as input for that particular iteration. For the subsequent iteration you are going to get a value higher than the value that you used for the previous iteration, isn't it? So that is how Ajk will be definitely higher than Cjk minus 1, right. Instead, if Cjk minus 1 is larger than Aj, then you will get a reducing effect because denominator is larger, right. So that is how we iteratively adjust the trip attraction value and give the adjusted value as initial trip attraction value for subsequent iterations, and this iterative process is continued until your calculated value of attraction and the desired value are matching to a significant extent. Okay. This is how we just adjust the trip attraction value for subsequent iterations. Let us stop here and recollect what we did today. We essentially understood the structure of the gravity model for trip distribution in this class, and we also know how the trip production constraint is introduced in the gravity model formulation to make sure that while you are distributing the trips, trip production values for the zones are not affected and only trip attraction values are influenced by the distribution process. And finally, we have discussed about a methodology to adjust the trip attraction values also to get the desired or actual observed values of trip attraction for each of the traffic zones, so that you actually distribute the trips based on the effect of the causal factors without affecting the basic information related to trip production and trip attraction of the traffic zones. We will continue our discussion in the next class.